The last cargo ship from Earth touches down on the Martian surface. Inside are filters, seeds, medicine, circuit boards, and 17 months of emergency rations. The crew unloads everything in silence because they already know what Mission Control confirmed 6 hours ago. No more ships are coming, not next year, not ever. The supply chain that kept them alive across roughly 34 million miles of vacuum has just been severed. They have oxygen generators, water recyclers, solar panels, a nuclear reactor, a greenhouse, and 41 human beings. They also have a planet that wants every single one of them dead. Not with a dramatic explosion, with patience. Mars does not need to attack a colony. It just needs to wait for one system to fail that no one on that planet can fix. If this kind of science keeps you watching, a like and a subscribe genuinely help this channel keep going. Now, are you comfortable? Let's begin. Picture a cargo lander settling onto red dust. Its landing legs crunch into the surface. Steam vents from its underside. Around it, a small collection of pressurized modules sits connected by the short tunnels, half buried under mounds of Martian soil piled there for insulation. A few hundred meters away, rows of solar panels stretch across the ground like dark mirrors angled toward a sun that looks noticeably smaller than the one you're used to. Beyond the panels, a squat cylindrical structure houses a nuclear fission reactor, its quiet hum the only reason anything here works at all. This is the colony. 41 people, 6 pressurized habitat modules, 1 greenhouse dome, 2 rovers, a medical bay that doubles as a dental clinic, a fabrication workshop with a set of 3-dimensional printers, storage bays filled with sealed crates of food, filters, spare parts, medical supplies, electronic components, batteries, seeds, chemical reagents, and more tools than most hardware stores on Earth carry. This final cargo lander is the last delivery, not the last one this year, the last one. The supply chain from Earth, the invisible lifeline that made this settlement possible, has been severed. The reason does not matter for the purposes of this story. Maybe it was political. Maybe it was economic. Maybe something happened back on Earth that made interplanetary logistics impossible for the foreseeable future. What matters is the result. No more ships, no more spare parts arriving in labeled crates, no more fresh seeds, no more updated medical kits, no more circuit boards manufactured in factories on another planet and sent across tens of millions of miles of vacuum. Everything this colony will ever have is either already inside those habitat walls or buried somewhere beneath the Martian surface, waiting to be extracted, processed, and turned into something useful by machines that were themselves built on Earth. That last detail is the one that changes everything. To understand what happens next, you need to understand what the colony is actually sitting on. Not in a geological sense, although we will get to that. In a systems sense, what does a Mars colony depend on minute by minute to keep its people alive? The answer is a list so long and so interconnected that even the engineers who designed these systems struggle to hold the full picture in their heads at once. Start with the air. The atmosphere of Mars is not just unbreathable, it is actively hostile to human lungs. Roughly 95% carbon dioxide. Less than 1% of Earth's atmospheric pressure at the surface. If you stepped outside without a suit, you would not suffocate in the way most people imagine. The moisture on your tongue and in your eyes would boil off first because at that pressure, liquid water cannot exist. Your lungs would not be able to exchange gas. Consciousness would last somewhere between 15 and 30 seconds. Death would follow within a few minutes, This is not a planet with thin air. This is a planet with almost no air at all, and what little air exists would poison you. Inside the habitat, the life support system maintains a breathable atmosphere by doing several things simultaneously. It generates oxygen. It removes the carbon dioxide that the crew exhales. It monitors nitrogen levels, humidity, temperature, and trace contaminants. It filters particulates. It regulates pressure. Each of these functions depends on specific hardware. Fans, pumps, chemical scrubbers, electrolysis units, sensors, control software, wiring, seals, and valves. Every one of those components was manufactured on Earth. Now consider temperature. The average surface temperature on Mars is around -60 degrees Celsius. That is roughly -80 degrees Fahrenheit. At the poles, winter temperatures can drop below -120 degrees Celsius. Even near the equator, a summer afternoon might reach a relatively mild 0 degrees Celsius, but by nightfall, the temperature plunges back well below freezing. The atmosphere is so thin it holds almost no heat. The temperature swings between day and night can exceed 70 degrees Celsius in a single rotation. The habitat modules handle this with insulation, heating systems, and thermal regulation powered by the colony's energy grid. That grid runs on two sources: a nuclear fission reactor, likely a small modular design similar to what NASA has been developing under its kilopower program, provides the baseline. Solar panels supplemented during the day when dust is not blocking the light. Both systems require maintenance, both degrade over time, and both are the single thread from which every other system hangs. Lose power and everything that depends on it fails simultaneously. Every system described so far, heating, air processing, water recycling, food production, medical monitoring, runs on electricity. Power is not one system among many. It is the system beneath all the others, and without it the colony has hours, not days. Then there is water. A human being needs roughly 1 gallon of water per day for drinking, food preparation, and basic hygiene. For 41 people, that is 41 gallons per day. Over a year, that is nearly 15,000 gallons. The colony cannot carry that much in reserve. It relies on recycling. The International Space Station, humanity's most successful experiment in closed-loop life support, has demonstrated water recovery rates of up to 98% using its environmental control and life support system. That number is extraordinary. It means that out of every 100 pounds of water the crew starts with, only 2 pounds are lost, and the rest keeps cycling. But 2% loss is not zero. Over months and years, that 2% accumulates. On the International Space Station, the loss is made up by resupply missions from Earth. A Mars colony cut off from Earth does not have that option. This is where Martian resources enter the equation. Mars has water. Not liquid water on the surface, because the atmospheric pressure is too low for liquid water to exist there. But water ice is buried beneath the surface across large regions of the planet. NASA's subsurface water ice mapping project has identified significant ice deposits in the mid-latitudes. Areas where landing is feasible and ice is accessible within meters of the surface. The colony could, in theory, extract this ice, melt it, purify it, and feed it into the recycling loop to compensate for losses. In theory. In practice, extracting subsurface ice on Mars means drilling or excavating frozen ground in a near vacuum environment at temperatures far below freezing, transporting the ice to a processing facility, melting it, removing contaminants including the toxic perchlorate salts that permeate Martian soil, and then integrating it into a water system that was designed and built on another planet. Every step in that chain requires functioning machinery. We have not even talked about food yet, or medicine, or what happens when a spacesuit develops a leak in the joint seal and the only replacement was in a crate that was supposed to be on the next ship. This is the nature of the problem. It is not one emergency. It is hundreds of dependencies layered on top of each other, each one manageable as long as the others hold, each one potentially fatal the moment it cannot be maintained. Think of it this way. On Earth, you depend on systems you never see. The water treatment plant across town, the power grid that stretches across entire continents, the global shipping network that puts food on shelves and medicine in pharmacies, the factories that manufacture everything from light bulbs to antibiotics. You depend on millions of people doing millions of specialized jobs in a web of production so vast that no single person understands more than a tiny fraction of it. A Mars colony has to replicate the essential outputs of that entire web with 41 people and whatever they brought with them. But the colony does carry something beyond physical tools and stockpiled materials. It carries knowledge, stored on hardened servers and backed up across multiple redundant drives, is a digital library containing technical manuals for every system in the habitat, repair procedures, engineering schematics, agricultural databases, medical references covering diagnosis, surgery, pharmacology, and dentistry, manufacturing specifications for components the colony might need to fabricate, metallurgical data, chemical process guides. The entire library represents the distilled expertise of thousands of specialists on Earth, researchers, engineers, doctors, and agronomists who spent careers mastering narrow fields, all compressed into data that a crew of 41 generalists must interpret and apply correctly to problems those specialists never anticipated. This library is arguably the colony's most valuable non-physical asset. It is the collective memory of an industrial civilization, stored in digital form. And it is indispensable, up to a point, because a library is only useful if someone alive can read it, understand it, and translate its contents into action for the specific failure they are facing. A repair manual for a water pump assumes the reader has the replacement part the manual specifies. When that part does not exist, and was never included in the manifest because the designers assumed resupply would always be available, the manual becomes a description of a solution the colony cannot execute. The crew must then improvise beyond the manual, using judgment, practical experience, and whatever materials happen to be on hand, materials the original engineers never intended for the purpose. That improvisation is where human skill becomes irreplaceable, and where every individual crew member's depth of understanding matters far more than any stored document. And there is another dimension to the colony's isolation that shapes every operational decision from the first day. Even if Earth is still listening, even if communication has not been cut alongside the supply line, the colony is functionally alone in every crisis. A radio signal from Mars to Earth travels at the speed of light and takes between 4 and 24 minutes to arrive depending on orbital positions. A round-trip exchange, question and answer, takes between 8 and 48 minutes at minimum. That does not include the time an engineer on Earth needs to analyze the problem, consult colleagues, and formulate advice. In practice, this means that a crew member describing a system failure to mission control must wait at least a quarter of an hour before any response begins to arrive. During a pressure leak or a reactor warning, a quarter of an hour is an eternity. By the time Earth hears about the problem, the crew has already made the decision, for better or worse. Mission Control becomes a consulting service operating on a time delay so severe that it cannot participate in real-time problem solving. It can review what happened afterward. It can offer guidance for the next occurrence. But in the moment when the alarm sounds and someone must act, the colony is alone with its training, its library, and the experience of whatever crew members happen to be in the room. The International Space Station is the closest comparison we have, and it is a humbling one. The station typically supports a crew of 6 to 7 people. It orbits only about 400 kilometers above Earth's surface. It is resupplied every few months by cargo vehicles that take less than a day to arrive. It has direct communication with Mission Control with only a few seconds of signal delay. If something goes critically wrong, an emergency evacuation can return the crew to Earth within hours using the Soyuz or Crew Dragon capsules permanently docked to the station. Even with all of those advantages, the station has experienced serious system failures that required either urgent resupply or creative improvisation with limited materials. The toilet has broken repeatedly. The water recycling system has needed replacement components sent up from Earth. Ammonia leaks, computer failures, and cooling system malfunctions have all required intervention. In 2007, a critical computer failure knocked out navigation, oxygen generation, and carbon dioxide removal simultaneously. The crew was never in immediate danger of death because they were 400 kilometers from Earth, not tens of millions of miles. A Mars colony has none of those safety nets. The nearest help is between 6 and 24 months away, depending on where Earth and Mars are in their respective orbits. Communication operates on the same severe delay already described, far too slow for real-time crisis support. There is no emergency evacuation capability. If the water recycler fails on the station, a replacement part can be on the next cargo run. If it fails on Mars, the colony either fixes it with what it has or begins losing water it cannot replace. Now consider the Antarctic research stations, a comparison that appears frequently in discussions about Mars settlement, and for good reason. McMurdo Station, the largest permanent settlement on the Antarctic continent, supports roughly 1,000 people during the summer season and around 200 during the harsh polar winter. It has heated buildings, a power plant, a medical clinic, a fire station, a harbour, and even a rudimentary road network. McMurdo is located on the most inhospitable continent on Earth. Winter temperatures can reach negative 50 degrees Celsius. The station is cut off from resupply during the winter months when sea ice and darkness make access impossible. The people who winter over at McMurdo are among the most isolated humans on the planet for that stretch of time. And yet, McMurdo is a paradise compared to Mars. The air outside McMurdo is breathable. The pressure is normal. Liquid water exists nearby, even if it is frozen most of the year. The crew can walk outside in heavy clothing without a pressure suit. If something goes catastrophically wrong, an emergency flight can reach the station from New Zealand in a matter of hours during the summer, and even during winter, an evacuation flight is theoretically possible in extreme circumstances. It has been done. McMurdo also depends entirely on annual resupply from the outside world. Fuel, food, medical supplies, construction materials, spare parts, and personnel all arrive by ship and aircraft during the Antarctic summer. Without that resupply, McMurdo would not last a full year. Not because the buildings would collapse, not because the power would fail immediately, but because the station consumes things it cannot produce locally. It eats through fuel, food, and medical stores at a rate that outpaces any possible local replacement. When the stockpiles run out, the station becomes uninhabitable. Every Antarctic station on the continent operates the same way. Every submarine in the ocean operates the same way. Every offshore oil platform, every aircraft carrier, every remote outpost humanity has ever built operates the same way. They are supplied. Their survival depends on a chain that leads back to the industrial infrastructure of civilization. A Mars colony is an outpost at the end of the longest supply chain ever constructed. And we are asking what happens when that chain breaks. To frame the answer, it helps to think about survival not as a single yes or no question, but as a series of layers. Each layer represents a category of need. Each layer has a different timeline for becoming critical. And each layer interacts with the others in ways that can turn a manageable problem into a cascading crisis. The first layer is the most immediate. Pressure, oxygen, carbon dioxide removal, temperature, and power. These are the things that will kill you in minutes to hours if they fail. A habitat breach, a total power failure, a runaway carbon dioxide buildup. These are the emergencies that dominate the first weeks and months after resupply stops. They are dramatic. They are the scenarios that science fiction tends to focus on. And they are, in some ways, the easiest layer to manage because the colony was designed to handle them. Redundant systems, backup generators, emergency sealant kits, and well-drilled emergency procedures can keep this layer intact for a significant period of time. The second layer operates on a longer timeline. Food production, water extraction, waste processing, and the slow degradation of recycling systems. These are the things that will kill you in months to a few years if they are not sustained. A crop failure in the greenhouse. A gradual decline in water recovery efficiency as filters age and membranes degrade. A nutrient deficiency that builds slowly until it causes irreversible health damage. These problems are less dramatic but more insidious because they do not announce themselves with alarms. They creep. The third layer is the one that determines whether the colony survives for years or for decades. Spare parts, electronics, machinery, precision components that wear out through normal use and cannot be manufactured locally without industrial infrastructure that does not exist on Mars. This is where the colony's fate is truly decided, not in the first emergency, in the slow grinding erosion of systems that were built to last 5 years, or 10 years, or 20, but not forever. And not without the factories that made them. The fourth layer is human. Medicine, surgery, dentistry, mental health, reproduction. The biological realities of keeping a population of 41 people functional over years and decades without access to a hospital, a pharmacy, or a specialist who has spent a career mastering one narrow branch of medicine. Each of these layers will be the focus of what follows, but the critical insight is this. The layers are not separate, they are a single interconnected system. The power grid supports the life support system, which supports the crew, which maintains the greenhouse, which produces the food, which sustains the crew, which repairs the power grid. Cut any link in that loop, and the effects propagate in every direction. A well-prepared colony, generously stocked, intelligently designed, and crewed by people trained across multiple disciplines, would not die in the first week without Earth. It would not die in the first month. It might not die in the first year. But every day, every week, every month that passes without resupply, the margins get thinner. The backup parts get used. The stockpiles shrink. The machines get older. And the colony moves one step closer to the moment when something essential fails and no one on that planet has the means to fix it. That moment is not an explosion. It is not a Hollywood disaster. It is a technician opening a storage locker, looking for a replacement pressure seal, and finding the shelf empty. What comes next is not a question of if the colony will face that moment. It is a question of when. And the answer depends entirely on what sits between the colony and the Martian surface in the most immediate layer of survival. The thin engineered barrier of pressure, breath, water, and power that is the only thing standing between 41 human beings and one of the most lethal environments in the known solar system. We're going to walk through that barrier system by system, and you will see exactly how fragile each piece is. The walls of a Mars habitat are not thick. Depending on the design, the pressure shell might be a composite layered material no more than a few centimeters across. Behind that shell is the difference between life and the death we already described. The Martian atmosphere exerts a surface pressure of roughly 600 pascals. Earth's atmosphere at sea level pushes down at about 101,325 pascals. That means Mars has less than 1% of the atmospheric pressure you are feeling on your body right now. The pressure difference between inside and outside a habitat is not a number on a gauge. It is a physical force. Every square centimeter of wall, window, and hatch is being pushed outward by air that wants to escape into a near vacuum. The structure holds because it was engineered to hold. But engineering has tolerances, and tolerances have limits. And on Mars, those limits are tested every second of every day by the largest sustained pressure differential any inhabited structure has ever been asked to maintain. Inside the habitat, the air pressure is maintained at something close to Earth, normal, or more likely at a reduced level, comparable to a high-altitude city to lessen the structural stress on the walls. Either way, the habitat is an inflated vessel on the surface of a world that wants to pull it apart. This means every seal matters, every gasket around a hatch, every viewport frame, every junction where one module connects to the next through a pressurized tunnel, every point where a pipe, a wire, or a ventilation duct passes through the hull. Each of these is a potential leak point. And on Mars, a leak is not a maintenance annoyance. It is an event that, if it grows fast enough, can depressurize a module before the crew can respond. Habitat designers plan for this. Modules are segmented so that a breach in one section can be sealed off without losing the entire structure. Emergency bulkheads can close. Leak detection sensors monitor pressure differentials continuously. Repair kits with adhesive patches and sealant compounds are stored at multiple points throughout the habitat. These measures are effective for small punctures and slow leaks. A micrometeorite impact, a fatigue crack in a viewport seal, a failed gasket around an airlock door. All of these can be patched if caught early and if repair materials are available. The problem is the word if. Every patch uses material. Every sealant compound has a shelf life. Every spare gasket is one fewer in the inventory. On Earth, if you patch a leaking pipe, you can order a new fitting from a supply catalogue and have it delivered by the end of the week. On Mars, without resupply, The sealant you use today is sealant you will not have next year. The habitat is aging. The Martian environment, with its extreme temperature swings between day and night and its abrasive dust, accelerates that aging. The seals that were rated for 10 years on Earth might last 7 on Mars, or 5. No one knows for certain because no pressurized structure has ever been tested in the Martian environment for that duration. Maintaining pressure is the most basic requirement. Without it, nothing else matters. But pressure alone does not keep you alive. You also need to breathe. The air inside the habitat must contain enough oxygen for 41 pairs of lungs. A resting human consumes roughly 360 liters of oxygen per day. That number nearly doubles during sustained physical exertion. And colonists maintaining a Mars habitat will not be sitting still. They will be hauling equipment, operating drills, repairing machinery, and conducting the relentless physical work that keeping a settlement alive demands. Call the average daily consumption roughly 1 kilogram of oxygen per person. For 41 people, that is 41 kilograms of oxygen per day, every day without exception. On Earth, this number is meaningless. The atmosphere contains roughly 1.2 quadrillion metric tons of oxygen, replenished continuously by photosynthesis across every ocean surface and every forest on the planet. On Mars, oxygen makes up approximately 0.13% of the atmosphere. It is there technically, but in quantities so small, they might as well be zero for the purposes of human respiration. The colony generates its oxygen through 2 primary methods. The first is electrolysis of water, splitting water molecules into hydrogen and oxygen using electrical current. This is the same fundamental chemistry used on the International Space Station, where the oxygen generation system electrolyzes water to produce breathable oxygen for the crew. It is reliable, well understood technology, but it consumes water, which means the oxygen system and the water system are directly coupled. Producing more oxygen means using more water. Using more water means needing to extract more ice from the Martian subsurface, or accepting a declining water reserve. Every liter of oxygen the crew breathes has a cost measured in water they cannot drink. The second method is solid oxide electrolysis of carbon dioxide drawn directly from the Martian atmosphere. This is the technology demonstrated by MOXIE aboard NASA's Perseverance rover. MOXIE proved the concept works. It extracted carbon dioxide from the Martian air and split it electrochemically, producing oxygen at a purity of 98% or better. Over 16 operational runs between 2021 and 2023, it generated a total of 122 grams of oxygen. At its peak efficiency, it produced 12 grams per hour, twice NASA's original performance target. 122 grams, that is roughly 6 hours of breathable air for a single person sitting quietly in a chair. MOXIE was never designed to support a colony. It was a technology demonstration, roughly the size of a microwave oven, proving that the chemistry works in the actual Martian environment. A human-scale version would need to be approximately 200 times larger, and would require a dedicated power supply generating between 25 and 30 kilowatts just for oxygen production alone. The colony would need a MOXIE-derived system running at industrial scale, continuously, with all of its components. The intake compressor, the solid oxide electrolysis cells, the filtration system that keeps Martian dust from fouling the electrochemistry, the output separation system, the thermal management hardware that keeps the whole assembly at operating temperature, functioning without interruption. Each of those components is a manufactured item with a service life, and every one of them was made on Earth. But oxygen is only half the breathing equation. The other half is carbon dioxide. Even if the habitat has perfect oxygen levels, rising carbon dioxide will kill the crew. At concentrations above about 5%, carbon dioxide causes headaches, confusion, loss of consciousness, and death. A single person exhales roughly 1 kilogram of carbon dioxide per day. 41 people produce 41 kilograms of carbon dioxide per day that must be actively removed from the habitat air. The station uses a system called the Carbon Dioxide Removal Assembly, which passes cabin air over beds of a material called zeolite that absorbs carbon dioxide. When the beds are saturated, they are heated to release the carbon dioxide, which is then vented or processed. The system works, but the zeolite beds degrade over time. On the station, replacement canisters are sent up from Earth. On Mars, the colony either finds a way to regenerate or manufacture its own absorbent material, or it watches carbon dioxide levels slowly creep upward as the scrubbing capacity declines. There are alternative approaches. Lithium hydroxide canisters react chemically with carbon dioxide and are used in spacecraft and submarines, but they are single use. Once the chemical reaction is complete, the canister is spent. Without a source of lithium hydroxide, they are a finite resource. Biological carbon dioxide removal using plants in the greenhouse is theoretically attractive, but the volume of plant matter required to scrub 41 kilograms of carbon dioxide per day is far larger than most habitat greenhouse designs can accommodate. Plants help. They're not sufficient on their own. There is one more chemical process that bridges the gap between carbon dioxide management and water recovery, and it deserves attention because it represents one of the colony's most important closed-loop opportunities. The Sabatier reaction combines carbon dioxide with hydrogen at elevated temperatures in the presence of a nickel or ruthenium catalyst to produce methane and water. The chemistry is well understood and has been studied for over a century. SpaceX's entire Mars return fuel architecture is built around a version of it. For the colony, the Sabatier process offers two outputs that matter enormously. The water it produces feeds back into the life support loop, partially compensating for the losses that accumulate in every recycling cycle. The methane it produces can be used as fuel for rovers, generators, or chemical feedstock for other processes. The inputs are available on Mars. Carbon dioxide makes up 95% of the atmosphere and can be captured directly. Hydrogen can be produced by electrolyzing water, which the colony is already doing for oxygen production. In principle, the Sabatier reactor takes a waste product the colony needs to remove from habitable air, combines it with a byproduct of oxygen generation, and produces two things the colony desperately needs. On paper, it is elegant. It closes part of the resource loop in a way that reduces dependence on external supply. In practice, the Sabatier reactor is another complex chemical system with its own maintenance demands. The catalyst beds that drive the reaction degrade over time as impurities in the input gases poison the catalytic surface. The reactor must operate at temperatures between roughly 300 and 400 degrees Celsius, requiring thermal management hardware that consumes power and contains components subject to fatigue. The gas handling system that feeds carbon dioxide and hydrogen into the reactor at the correct ratios and pressures includes valves, regulators, sensors, and piping that all age and can fail. And the catalyst itself, typically a nickel alloy deposited on a ceramic substrate, is a manufactured item that cannot be readily fabricated on Mars. When the catalyst loses activity, production drops. When it fails entirely, the colony loses both a water source and a fuel source simultaneously. These Sabatier processes real, proven chemistry. It will be part of any serious Mars colony design. But like every other system in the colony, it extends survival without eliminating dependence. It buys time. It does not buy independence. So the colony breathes through a combination of manufactured systems, each with a finite lifespan, each depending on components that degrade, and each coupled to other systems that have their own dependencies. This is the architecture of survival on Mars. Not a single solution, but a web of partial solutions layered together, each covering the gaps of the others, all of them slowly wearing down. Now consider the water system in detail. We have already established that the colony needs to recycle aggressively. Even at 98% recovery, 2% of the water passing through the system is lost every cycle. Some of that loss is chemical, water molecules broken down in processes like electrolysis for oxygen production. Some is physical, tiny amounts trapped in waste products, absorbed into materials, or lost through seals that are not perfectly tight. Some is biological, moisture that leaves the habitat through the airlock every time a crew member goes outside for a surface operation, carried on the outer layers of a spacesuit that returns drier than it left. 2% sounds trivial. It is not. If the colony starts with 10,000 litres of water in active circulation, 2% loss per complete cycle means 200 litres lost. How quickly those cycles occur depends on consumption rates and processing speed, but over the course of a year, the losses add up to a substantial fraction of the total supply. Without a way to replace that water, the system slowly drains. Martian ice is the replacement source, and the colony has the advantage of location. NASA's Subsurface Water Ice Mapping Project has confirmed that significant ice deposits exist in the mid-latitudes, some within a few meters of the surface. The Phoenix lander confirmed the presence of water ice just centimeters below the surface at its high-latitude landing site back in 2008. The evidence is strong. Mars has water. The question is whether the colony can get to it, extract it, and process it fast enough to stay ahead of system losses. Extraction means digging. On Mars, digging is not a simple operation. The regolith is a mixture of fine basaltic dust and larger rock fragments. In many locations, it is cemented together by perchlorate salts and other mineral deposits that make it harder than loose soil. Below the regolith, the ice may be mixed with rock in varying concentrations, not a clean sheet of frozen water, but a dirty amalgam that must be excavated, heated, and separated. The excavation equipment, drills, scoops, conveyors, heating chambers, all run on power from the colony's grid. They all have moving parts that wear out. They all operate in conditions of extreme cold, pervasive fine dust, and low gravity that changes the behavior of granular materials in ways that Earth-based mining equipment was never designed to handle. Martian dust is not like earthly sand. It is electrostatically charged, incredibly fine, and clings to every surface. It works its way into joints, abrades seals, coats optical sensors, and fouls mechanical systems. It is one of the most persistent engineering threats on Mars, and one of the hardest to mitigate over the long term. Once the ice is extracted, it must be purified. Martian water ice is not clean. It contains perchlorate salts at concentrations that are toxic to humans, even in small amounts. Perchlorates interfere with thyroid function, and can cause serious health effects with prolonged exposure. The colony must remove these contaminants before the water can enter the life support loop. Perchlorate removal requires either chemical treatment, specialized filtration, or biological remediation using engineered microorganisms that break perchlorates down into chloride and oxygen. Each of these methods requires consumable materials or living cultures that must be maintained. Every link in this chain, excavation, transport, heating, separation, purification, integration into the life support system, is a potential point of failure. And every point of failure is one that Earth cannot fix. Beneath all of these systems, supporting every one of them, is power. Power is not just another system on the list, it is the system. Without electrical power, the oxygen generators stop. The carbon dioxide scrubbers stop. The water recyclers stop. The heaters stop. The lights in the greenhouse go dark. The computers that monitor every other system go offline. The radios go silent. Power is the foundation on which the entire colony rests. And if it cracks, everything above it falls. The colony's primary power source is almost certainly a nuclear fission reactor. NASA has been developing small fission systems under programs with names like Kilopower and its successor efforts, designed to produce between 1 and 10 kilowatts of electrical power per unit. A colony of 41 people with industrial-scale life support, water processing, oxygen production, lighting, heating, computing, communications, and manufacturing needs would require somewhere in the range of 100 to several hundred kilowatts of continuous power, depending on the efficiency of the systems and the demands of resource extraction. Nuclear fission has enormous advantages for Mars. It operates continuously, day and night, regardless of weather. It does not depend on sunlight. It is not affected by dust storms. A well-designed reactor using highly enriched uranium fuel can run for years before the fuel is depleted. It is compact relative to its energy output. For a Mars colony, it is the closest thing to a guaranteed power source that current technology can provide. But a nuclear reactor is also one of the most complex machines ever built. Even small fission reactors contain precision-manufactured fuel elements, neutron reflectors, control mechanisms, heat exchangers, power conversion systems, radiation shielding, and cooling infrastructure. Every one of these components has a design life. The fuel itself, while long-lasting, is finite. The heat exchangers that transfer thermal energy from the reactor core to the power conversion system are subject to thermal cycling stress, corrosion, and material fatigue. The control mechanisms that regulate the nuclear reaction must function with extreme precision because the consequence of failure is not a blown fuse, but a potential meltdown or an uncontrolled shutdown that leaves the colony dark. On Earth, nuclear reactors are maintained by teams of hundreds of specialized engineers backed by an industrial supply chain that can produce replacement components on demand. On Mars, the reactor is maintained by whichever members of a 41-person crew have reactor training, using whatever spare parts were included in the original manifest. If a heat exchanger develops a crack, the colony does not call a manufacturer. It either repairs it with the materials on hand, or it watches its power output decline. Solar panels are the backup, and on Mars, they are a deeply imperfect one. Mars orbits roughly 1.5 times farther from the Sun than Earth does. By the inverse square law, the solar energy reaching the Martian surface is approximately 43% of what reaches Earth's surface. That alone cuts the output of any solar panel nearly in half compared to the same panel on Earth. Then there is the dust. Mars experiences dust storms that range from local events, covering a few hundred square kilometers, to global storms that can shroud the entire planet for months. In 2018, a global dust storm blanketed Mars so thoroughly that NASA's Opportunity rover, which had been operating on solar power for nearly 15 years, lost contact and never recovered. The storm reduced solar energy reaching the surface by more than 90% at its peak. For a colony depending on solar panels as a supplementary power source, a global dust storm is not just a nuisance. It is a slow-motion emergency that can last for weeks or months, during which the colony must survive entirely on its reactor and stored energy reserves. But a global dust storm does not only threaten the power budget, it threatens everything at once. To understand why, consider what week 3 of a major storm looks like inside the colony. The solar panels are producing almost nothing. Dust has been accumulating on their surfaces faster than any cleaning operation can address, and for the past 10 days, the crew has not been able to perform outside maintenance at all because wind-driven particulates reduce surface visibility to near zero, and the risk of suit damage from abrasion is too high. The colony is running entirely on nuclear power, and every kilowatt is being rationed. Non-essential lighting has been reduced. The fabrication workshop is powered down. The Sabatier reactor is running at half capacity because the power to heat it to operating temperature has been diverted to more immediate needs. That means water recovery from carbon dioxide processing has dropped, adding pressure to the water budget. Ice extraction has stopped entirely. The drilling and excavation equipment sits idle on the surface, its exposed components accumulating a fine coat of electrostatically charged dust that works its way into every joint and seal. When the storm clears and operations resume, the equipment will need inspection, cleaning, and in some cases repair before it can function. That maintenance will consume time and spare parts that the crew is already rationing. Inside the habitat, the air filtration system is under increased load. During a storm, Martian dust finds its way into the habitat at higher rates than normal. The fine particles driven by storm winds penetrate airlock seals more aggressively. Every suit that was used during the storm's early days, before outdoor operations were suspended, brought additional dust inside. The habitat's air filters are catching more particulates per hour than they were designed for at baseline operation. Filter replacement intervals have shortened. The inventory of replacement filters, already a finite resource, is being consumed faster than planned. The greenhouse is affected too. Even inside a pressurized, artificially lit growing environment, the storm matters. If any portion of the greenhouse relies on supplementary natural light through transparent panels, that light is gone. The LED grow lights are running on power diverted from other systems, and if the power budget forces a reduction in lighting hours, the plants respond. Photosynthesis rates drop, growth slows. The crop cycle that was carefully timed to produce a harvest at a specific week pushes later, and the stored food supply must cover the gap. The crew feels the storm psychologically in ways that compound the engineering pressure. The windows, if the habitat has any, show nothing but a featureless amber murk. The sense of isolation intensifies. Outdoor work, which despite its dangers provides a sense of agency and physical variety, is impossible. The crew is confined to the same corridors, the same modules, the same faces, with the additional stress of watching power margins shrink and system loads increase, tempers shorten, sleep quality declines in the dimmed lighting. The colony's psychological reserves are being drawn down at the same time as its physical reserves. Global dust storms on Mars are not rare events. They occur roughly every 3 to 4 Martian years, or approximately every 6 to 7 Earth years. A colony that survives for a decade will face at least 1, possibly 2. And each storm is not a single crisis, but a sustained multi-week stress test, applied to every system simultaneously. The kind of event that reveals exactly how thin the colony's margins have become. Even outside of major storms, ordinary Martian dust settles on solar panels continuously. Without regular cleaning, panel efficiency drops steadily. Cleaning requires either automated systems with their own maintenance needs, or crew time devoted to walking outside in spacesuits and manually wiping panels, a task that consumes the very energy it is trying to preserve and exposes crew members to radiation and suit wear. This brings us to a point that deserves a careful pause. Every system described so far, pressure maintenance, oxygen generation, carbon dioxide removal, the Sabatier process, water recycling, water extraction, purification, nuclear power, solar power, functions today. The technology exists. It has been demonstrated in space, in laboratories, and in some cases on the Martian surface itself. The colony is not depending on science fiction, it is depending on proven engineering. The question is not whether these systems work. The question is how long they work without the industrial civilization that created them. Consider what happens in year 2. The habitat seals have been patched twice. The sealant supply is noticeably lower than it was. One of the 3 oxygen-producing electrolysis units has developed an intermittent fault that the crew has been unable to fully diagnose. They have compensated by running the remaining 2 units at higher capacity, which accelerates their wear. The carbon dioxide scrubbers are still functioning, but the zeolite beds are losing absorption efficiency. And the crew has noticed that carbon dioxide levels in the sleeping quarters tend to creep slightly higher overnight than they did in the first year. The water recycler is holding at around 96% recovery, down from its initial 98%, because one of the filtration membranes is degrading and the replacement is the last one in storage. The solar panels are producing about 85% of their original output due to dust accumulation that the crew cannot fully remove. The nuclear reactor is stable, but a minor vibration in the power conversion unit has appeared in the monitoring data, suggesting a bearing or a shaft alignment issue that will eventually need attention. None of these problems is a crisis. Each one is manageable. The colony is still alive. The crew is still breathing. The water is still flowing. The lights are still on. If you visited the colony on this day, you might look around and conclude that things are fine. But an engineer would see something different. An engineer would see margins narrowing, redundancies being consumed, backup systems becoming primary systems, the distance between normal operation and failure shrinking in every subsystem simultaneously. Not because of one catastrophic event, but because of the relentless arithmetic of wear, degradation, and consumption in a closed system that cannot be restocked. This is the nature of the first survival layer. It is robust in the short term. It is engineered to handle emergencies. It is designed with redundancies that can absorb failures. But every redundancy that absorbs a failure is a redundancy that no longer exists for the next one. The colony starts with a safety margin and spends it down, day by day, the way a person lost in the wilderness burns through their supplies. The calories last longer if you ration carefully. But rationing does not create new food. The first layer of survival, pressure, breath, water and power, is the barrier between the colony and instant death. With stockpiled spares and careful maintenance, it can hold for months. With local resource extraction feeding water and carbon dioxide into the loop, it might hold for years, but it cannot hold forever. Not without the ability to manufacture the components it consumes. And while the crew is focused on keeping the air in their lungs and the water flowing through their pipes, a slower and more insidious threat is building in the greenhouse module where the colony's food supply is already showing signs of trouble. The plants are growing, but they are not growing well enough, and what is happening in the soil, or rather what is not happening, will test the colony's survival in ways that no amount of engineering can fully prepare for. The greenhouse module is the most psychologically important room in the colony. It is the only place where anything is green. The only place where the air smells like soil and leaf instead of recycled metal and plastic. The crew gravitates there during off hours, not just because it produces food, but because it is the only space on Mars that resembles home. When the first lettuce crop sprouted under the LED grow lights, people cried. It felt like proof that life could take root here. That feeling will not last. Growing food on Mars is not like farming on Earth. It is not even like growing food aboard the International Space Station, where astronauts have cultivated lettuce, radishes and chili peppers in small experimental chambers. Those were demonstrations. Nutritional supplements, morale boosters. The astronauts who grew those crops were eating meals prepared from food shipped up from Earth. The plants were a side dish, not a lifeline. For a colony cut off from resupply, the greenhouse is not a morale project. It is the difference between surviving and starving. A human being requires roughly 2,000 to 2,500 calories per day to maintain body weight under moderate activity levels. For colonists performing the physical labor of habitat maintenance, equipment repair, ice extraction, and spacesuit operations, the actual demand is likely closer to 3,000 calories per day. For 41 people, that is approximately 123,000 calories per day, every day, without interruption, without a single season off. To produce that many calories from plants alone, you need a substantial growing area. Estimates vary depending on the crop mix, light intensity, growing cycle length, and system efficiency. But most agricultural researchers studying closed environment food production put the figure at somewhere between 40 and 60 square meters of active growing area per person for a nutritionally complete diet. For 41 people, that means between roughly 1,600 and 2,500 square meters of greenhouse space, all of it pressurized, heated, lit, irrigated, and atmospherically controlled. Most Mars habitat concepts do not include that much greenhouse space, not even close. The initial colony is far more likely to have a few hundred square meters at best, supplemented by stored food reserves. Those reserves were calculated to bridge the gap between arrival and full agricultural productivity. They assumed that resupply ships would keep arriving to replenish what was consumed. Without resupply, the stored food becomes a countdown clock. Every meal that comes from a sealed packet is a meal that will never be replaced. The pressure to expand food production becomes intense within the first year. And this is where Mars begins to fight back in ways that are unique to this planet. You cannot simply scoop Martian regolith into a pot and plant seeds. The regolith is not soil. Soil, as it exists on Earth, is a living system. It contains organic matter, decomposing plant and animal material, fungal networks, bacterial colonies, and billions of microorganisms per handful that cycle nutrients, break down waste, retain moisture, and create the chemical environment that plant roots depend on. Martian regolith contains none of this. It is crushed volcanic rock, fine basaltic dust with no organic carbon, no nitrogen in biologically available form, and no microbial life. Worse, it is toxic. Perchlorate salts are distributed across the Martian surface at concentrations of roughly 1.5 to 5 grams per kilogram of regolith. Laboratory experiments have shown that perchlorate at these concentrations prevent seed germination entirely in regolith simulants. Even in enriched potting soil, perchlorate at 1% concentration severely restricts plant growth, reduces leaf area, and decreases biomass. The presence of perchlorate also increases the release of certain metals from the regolith, adding another layer of toxicity that persists even after the perchlorate itself is removed. The colony has options for dealing with this. The regolith can be washed with water to leach out the soluble perchlorates. Though this produces toxic wastewater that must be treated separately and consumes water the colony can barely spare. Thermal treatment, heating the regolith to approximately 400 degrees Celsius, can decompose perchlorates, but this requires significant energy. Biological remediation using perchlorate-reducing bacteria is promising, and a 2026 study confirmed that both thermal treatment and leaching with distillation are practical strategies, but each approach demands resources the colony will be rationing carefully. Even after perchlorate removal, the regolith is still not soil. It must be amended with organic matter, nitrogen sources, phosphorus, potassium, and trace minerals, all of which must come from somewhere. Composting human waste and inedible plant matter can provide some organic carbon and nutrients, but a closed system with 41 people and a small greenhouse does not generate enough waste biomass to convert thousands of square meters of dead rock into productive growing medium. The colony is trying to bootstrap an ecosystem from scratch on a planet where no ecosystem has ever existed, using resources it cannot afford to waste. Hydroponic and aeroponic systems avoid the regolith problem entirely by growing plants in nutrient-rich water solutions or mist. These systems are more water efficient, faster growing, and produce higher yields per square meter than soil-based agriculture. They are the most likely primary food production method for an early Mars colony, but they depend entirely on manufactured components: pumps, tubing, nutrient reservoirs, pH sensors, dosing systems, LED grow lights, fans, and control electronics. Every one of these is a manufactured item with a limited service life. The pumps wear out. The tubing degrades under constant moisture and nutrient exposure. The LED arrays lose intensity over thousands of hours of operation. The sensors drift out of calibration. The nutrient solutions must be precisely formulated and replenished with chemical stocks that were brought from Earth. When a hydroponic pump fails in a research greenhouse at a university on Earth, someone orders a replacement online and it arrives in 2 days. When a hydroponic pump fails on Mars without resupply, the colony either fabricates a replacement from available materials, cannibalizes a pump from another system, or watches a section of food production go offline. And then there is the scenario that keeps agricultural scientists awake at night: crop failure. Not a gradual decline in yield, a total loss. In a closed environment with limited genetic diversity, a single pathogen, a fungal infection, a bacterial blight, an insect infestation carried in on a seed stock can spread through an entire crop in days. On Earth, agriculture survives because it operates on a continental scale. If wheat rust destroys a harvest in one region, grain from another region fills the gap. A Mars greenhouse has no other region. There is no backup farm on the other side of the planet. There is no emergency food import from a neighboring country. If the potato crop develops blight and the colony's stored seed stock carries the same susceptibility, the potatoes are gone. Not for this season. Possibly forever. The historical precedent is worth lingering on. In the early 1990s, the Biosphere 2 experiment in Arizona attempted to create a sealed, self-sustaining ecosystem supporting 8 people, despite having 3.14 acres of carefully designed biomes, abundant sunlight, and a team of ecologists who had spent years preparing the system. The project experienced cascading agricultural failures. Crop yields fell short. Oxygen levels dropped so severely that supplemental oxygen had to be pumped in from outside, breaking the seal of the experiment. Carbon dioxide fluctuated unpredictably. Pollinating insects died off. The crew members, by the end of the 2-year mission, described themselves as having suffocated, starved, and gone mad. That was on Earth, with full atmospheric pressure outside, with a global ecosystem surrounding the structure, with the ability to break the seal and pump in air if things went critically wrong. Mars offers no such escape valve. But even if the greenhouse operates flawlessly, even if every crop produces exactly the yield the agricultural plan predicted, the colony still faces a nutritional crisis that calories alone cannot solve. This is the protein problem, and it is one of the most underestimated threats to long-term Mars survival. The crops best suited to closed environment agriculture are, almost without exception, high in carbohydrates and low in protein and fat. Potatoes, sweet potatoes, wheat, and rice are the caloric workhorses of any space agriculture plan, because they produce the most energy per square meter of growing area. They are reliable, they are well understood, and they are almost entirely starch. A human being cannot survive on starch alone. The body requires roughly 50 to 60 grams of complete protein per day to maintain muscle mass, organ function, immune response, and cellular repair. For colonists performing heavy physical labor in a low-gravity, high-radiation environment, the requirement is almost certainly higher. Protein deficiency does not kill quickly. It degrades. Over weeks and months, muscle wasting accelerates beyond what low gravity alone would cause. Wound healing slows, the immune system weakens, making every minor infection more dangerous. Cognitive function declines, hair thins, skin becomes fragile. The body, deprived of its essential building blocks, begins to consume itself. Fat is equally critical and equally difficult to produce in a greenhouse. Fats provide more than twice the caloric density of carbohydrates, and they are essential for absorbing vitamins, producing hormones, and maintaining neurological function. The crops that produce dietary fats, soybeans, peanuts, sunflower seeds, require growing conditions and space that a small Mars greenhouse may not be able to provide in sufficient quantity. The colony has a few options for protein, none of them comfortable. Soybeans are the most protein-dense crop that could realistically be grown in a closed system. They are versatile, they fix nitrogen in the soil if soil-based growing is attempted, and they provide both protein and oil. but they require significant growing area per kilogram of usable protein, and a soybean monoculture is exactly the kind of low-diversity agricultural system most vulnerable to a single disease wiping out the entire crop. Insect farming is a more space-efficient protein source. Black soldier fly larvae, mealworms, and crickets can be raised on organic waste and inedible plant matter, converting biomass the crew cannot eat into biomass it can. Mealworms were used as the primary protein source in China's Lunar Palace experiment, a closed ecosystem simulation where they consumed the parts of plants that the human crew could not eat and were in turn consumed by the crew. Insect farming requires minimal space, minimal water, and produces protein at a fraction of the resource cost of any vertebrate animal. It is almost certainly part of any serious Mars food plan. But insect colonies are living systems with their own vulnerabilities. They can be killed by temperature fluctuations, contaminated by the pathogens, or simply fail to reproduce if conditions shift outside their tolerance range. Maintaining a healthy insect colony requires environmental control, feeding schedules, and monitoring, all of which demand crew time and functioning equipment, in a habitat where both are already stretched thin. Microalgae represent another option. Organisms like spirulina and chlor-Lr are extraordinarily efficient at converting light, carbon dioxide, and simple nutrients into protein-rich biomass. They grow faster than any terrestrial crop. They can be cultivated in transparent tubes or tanks that take up far less space than a traditional growing bed. And their nutritional profile includes not just protein, but essential fatty acids, vitamins, and minerals that the rest of the colony's diet may lack. The difficulty is that algae cultivation at scale requires bioreactors, specialized transparent containment vessels with precise temperature, lighting, and nutrient control. These are once again manufactured systems with finite lifespans. The tubes cloud over time, the pumps that circulate the growth medium wear out. The nutrient inputs must be carefully balanced, and if a contaminating organism enters the culture, it can crash the entire production batch in days. Each of these protein sources, soybeans, insects, algae, is viable in theory and fragile in practice. The colony would likely rely on all three simultaneously, spreading its risk across multiple systems. But every additional food system adds complexity, demands crew attention, and creates new failure modes. The crew is not running one farm. It is running half a dozen interlocking biological systems, each with different needs, different vulnerabilities, and different consequences if it fails. And alongside the protein problem sits a quieter danger that most discussions of Mars food production overlook entirely: micronutrient deficiency. Even a colony producing enough calories and enough protein can be slowly killed by what its diet is missing. Vitamin C is the most immediate concern. Without a reliable source of fresh fruits or vegetables rich in ascorbic acid, the crew develops scurvy. The early symptoms are subtle: fatigue, aching joints, small bruises that appear without clear cause. Over weeks, the symptoms intensify. Gums swell and bleed. Old wounds reopen. New wounds refuse to heal. Left untreated, scurvy is fatal. On Earth, it is almost unheard of in modern populations because vitamin C is abundant in common foods. On Mars, if the greenhouse loses its capacity to produce the specific crops that provide it, the crew begins to deteriorate within months. Vitamin B12 presents a different kind of problem. It is found almost exclusively in animal-derived foods and certain microorganisms. A purely plant-based diet with no supplementation will eventually produce B12 deficiency, which causes neurological damage, anemia, and cognitive impairment. The colony's stored vitamin supplements will cover this for a time, but supplements expire. Without a biological source of B12, whether from insect farming, algae cultures, or bacterial fermentation, the crew faces irreversible neurological harm over a period of years. Iron deficiency leads to anemia, compounding the fatigue and weakness that low gravity and radiation exposure already impose. Vitamin D deficiency, a near certainty on a world where sunlight reaching the surface carries dangerous ultraviolet radiation, and the crew spends most of its time underground or inside shielded modules, weakens bones that are already losing density from reduced gravity. Zinc deficiency impairs immune function in a closed environment where infectious disease is already a heightened risk. The colony's ability to manage these deficiencies depends on the diversity and health of its food production systems. Every crop lost narrows the nutritional spectrum available. Every failed insect colony removes a protein and micronutrient source. Every crashed algae culture takes essential fatty acids and B vitamins off the table. The crew does not experience these losses as sudden hunger. It experiences them as a slow, progressive weakening of the body's systems, a degradation of physical and cognitive capacity that makes every other task harder and every other problem more dangerous. Assuming the colony manages to keep food production running, the next layer of survival rises into view. The machinery itself. Not the life support systems already covered, but everything else. The physical infrastructure that the colony depends on to function as something more than a group of people slowly consuming stored supplies in a sealed room. Start with spacesuits. Every task performed outside the habitat requires a pressurized extravehicular activity suit. Ice extraction, solar panel maintenance, external habitat repair, rover operations, geological surveying for mineral resources, antenna maintenance, all of it requires someone to put on a suit and step outside. Mars suits do not yet exist in a flight-ready form, but the design requirements are well understood. They must maintain pressure, provide oxygen, remove carbon dioxide, regulate temperature, protect against radiation, resist abrasion from Martian dust, and allow enough mobility for physical labor. Each suit is an engineering marvel composed of dozens of materials, hundreds of components, and multiple subsystems including fans, pumps, heaters, communication electronics, helmet visors, gloves, boots, and joint bearings. Every component wears. The joint bearings that allow an astronaut to bend their elbows and knees are subject to constant stress and dust infiltration. Martian dust is electrostatically charged and extraordinarily fine, measured in particles just a few micrometers across. It works its way into every seam. Apollo astronauts on the moon, who spent only hours outside, reported significant dust contamination of their suit joints after a single excursion. Lunar dust damaged seals, scratched visors, and caused respiratory irritation when tracked back inside the lunar module. Martian dust is finer, more chemically reactive, and the colony's crew will be spending orders of magnitude more time outside than any Apollo mission. And Martian dust carries a hazard that lunar dust does not. It is laced with the same perchlorate salts that contaminate the regolith. Every spacesuit that returns through the airlock carries a film of this dust on its outer surfaces, in its joint creases, and embedded in the texture of its materials. Airlock protocols include dust removal procedures, brushing, vacuuming, and blowing compressed air across suit surfaces before the crew member enters the habitat. But no cleaning protocol removes all of it. Studies of dust mitigation in analog environments have consistently shown that fine particles migrate through barriers. They become airborne inside the habitat. They settle on surfaces. They are inhaled. Perchlorate particles in the lungs are not merely an irritant. Perchlorates interfere with iodine uptake by the thyroid gland. Chronic low-level inhalation exposure, the kind that would accumulate over months and years of daily suit operations, could produce subclinical thyroid dysfunction across the entire crew. Reduced thyroid function affects metabolism, energy levels, cognitive sharpness, and the body's ability to regulate temperature, which is already under stress in an artificially heated environment. The effects will be subtle. The crew might not recognize them as a distinct medical problem. They would manifest as a general, creeping decline in performance that makes everything slightly harder, and every error slightly more likely. This is the dust-to-lung pathway, and it connects suit maintenance, airlock design, air filtration, and medical supply consumption into a single thread of risk. The air filters that protect the crew from inhaling Martian particulates are themselves consumable items with finite lifespans. As they load up with captured dust, their airflow resistance increases. The fans pushing air through them work harder. The fans draw more power. The power budget tightens. And if the filters are not replaced, the particulate concentration in the habitat air rises, slowly, invisibly, carrying perchlorates with it. Suit maintenance becomes a continuous operation. Seals must be inspected and replaced. Visors must be polished or swapped. Gloves, which take the most abuse, must be cycled through a rotation of repair and replacement. The colony's suit inventory is finite. When the last replacement glove has been used, someone has to figure out how to fabricate a new one from available materials, or the colony's ability to perform outside work begins to shrink. The same logic applies to rovers, the pressurized vehicles that extend the colony's operational range across the Martian surface. Rovers have wheels, axles, suspension systems, electric motors, batteries, navigation systems, communication antennae, thermal regulation, and pressure seals. Each of these components operates in an environment that Earth-based vehicles were never designed to endure. The abrasive dust, the extreme cold, the low atmospheric pressure that eliminates convective cooling, the ultraviolet radiation that degrades polymers and rubber compounds. All of it accelerates wear. Consider the batteries alone. Lithium-ion batteries, the most likely power storage technology for a Mars rover, degrade with every charge-discharge cycle. Over hundreds of cycles, their capacity diminishes. After a few thousand cycles, depending on the depth of discharge and thermal management, they may retain only 70 or 80% of their original capacity. Eventually, they must be replaced. The colony brought spare battery packs. When those are exhausted, the rovers begin to lose range. Shorter range means less territory can be covered for ice extraction, geological exploration, and maintenance of remote equipment. The colony's operational radius contracts. Now multiply this pattern across every mechanical and electronic system in the colony. Pumps, valves, fans, circuit boards, sensors, wiring harnesses, connectors, bearings, filters, gaskets, heat exchangers, solar panel inverters, communication transceivers. Each one has a design life. Each one was manufactured by a specialized factory on Earth using materials sourced from a global supply chain. Each one, when it fails, presents the colony with a question that has no comfortable answer. Can we fix it with what we have? Three-dimensional printing is often invoked as the solution to the spare parts problem, and it does solve part of it. A three-dimensional printer loaded with the right feedstock can produce structural components, brackets, housings, simple tools, and even some replacement parts for mechanical systems. The colony would almost certainly carry multiple printers and a supply of printing materials including various polymers and potentially metal powders. But three-dimensional printing cannot produce everything. It cannot fabricate a microprocessor. It cannot print a lithium-ion battery cell. It cannot manufacture a precision ball bearing with the surface finish tolerances required for a high-speed rotating shaft. It cannot synthesize a pharmaceutical compound. It cannot produce optical-grade glass for a replacement visor. It cannot create the specialized elastomer compounds used in pressure seals rated for vacuum exposure. The list of things a three-dimensional printer cannot make is far longer than the list of things it can. And the items on that list are precisely the ones that tend to be the most critical and the most difficult to substitute. This is the gap that separates a supplied outpost from an independent colony. The outpost receives the things it cannot make. The colony must either make everything or accept that some capabilities will eventually be lost forever. And losing a capability on Mars does not mean doing without a convenience. It means losing the ability to perform a function that other systems depend on. Lose the ability to fabricate pressure seals, and the habitat begins to leak faster than it can be patched. Lose the ability to replace circuit boards, and the automated monitoring systems go blind. Lose the ability to repair spacesuit joints, and outside work becomes impossible. Each lost capability removes a piece from the structure, and the structure has no spare pieces to absorb the loss. Then there is medicine. 41 people living in a confined, physically demanding, radiation-exposed environment for years will experience the full range of human medical problems. Injuries from equipment handling and construction work, burns from electrical faults or thermal systems, lacerations from sharp metal edges, fractures from falls in a habitat where the lower gravity tempts people into movements that human bones were not designed for, infections from minor wounds that turn serious in an enclosed environment where antibiotic-resistant organisms could develop and spread among a small population with no ability to quarantine effectively. Dental emergencies are a near certainty over any multi-year period. Cracked teeth, abscesses, impacted wisdom teeth, all require intervention. On Earth, you go to a dentist who has been trained for years and has access to specialized equipment, anesthetics, antibiotics, and imaging technology. On Mars, dental care is performed by whichever crew member received the most dental training during mission preparation, using a limited kit of instruments and a dwindling supply of dental materials. Surgical emergencies present an even starker challenge. Appendicitis, kidney stones, internal bleeding from a trauma injury, an ectopic pregnancy. These are conditions that on Earth are treated in operating rooms by trained surgeons, supported by anesthesiologists, nurses, sterile environments, imaging equipment, blood supplies, and post-operative care facilities. A Mars colony has none of this at hospital standard. It has a medical bay with the best equipment that could be packed into the available mass allowance, a crew member with surgical training, and a finite supply of surgical consumables, anesthetics, sterile dressings, sutures, and medications. Medications expire. Most pharmaceuticals have shelf lives of 1 to 5 years. Some can be extended with careful storage, but on Mars, storage conditions are imperfect. Temperature fluctuations, radiation exposure, and the passage of time all degrade chemical compounds. The colony's pharmacy is a wasting asset. Every pill taken is a pill that cannot be replaced. Every course of antibiotics administered is one fewer available for the next infection. The crew knows this. Every medical decision becomes a calculation not just of the patient's immediate need, but of the colony's long-term survival. Chronic conditions develop. Over years, the effects of lower gravity, estimated at roughly 38% of Earth's, accumulate. Bone density decreases. Muscle mass declines despite exercise protocols. Cardiovascular deconditioning progresses. Vision changes, potentially related to altered intracranial pressure in lower gravity environments, have been documented in astronauts on long-duration missions aboard the International Space Station. On the station, these conditions are managed because the astronauts return to Earth. On Mars, there is no return. The crew lives with these changes, and the medical team manages them with whatever resources remain. Radiation exposure adds a layer of long-term medical risk that is difficult to quantify precisely, but impossible to ignore. Mars has no global magnetic field. Its thin atmosphere provides only modest shielding against galactic cosmic rays and offers limited protection during solar particle events. NASA's career radiation exposure limit for astronauts is 600 millisieverts. Studies estimate that a Mars mission could expose crew members to radiation levels that approach or exceed this limit, with central mortality risk estimates of 5 to 10% for a full Mars mission and upper confidence bounds near 20% for combined cancer and cardiovascular disease risk. On a permanent colony without the option of returning to Earth, these lifetime exposure limits become meaningless because the exposure never stops. It accumulates year after year, raising cancer risk, increasing cardiovascular disease probability, and potentially affecting cognitive function. Habitat shielding helps. Burying modules under regolith blocks a significant portion of cosmic radiation. Storm shelters with additional shielding can protect the crew during solar particle events. But no practical shielding completely eliminates galactic cosmic ray exposure. The secondary particles produced when high-energy cosmic rays interact with shielding material can themselves be biologically damaging. The crew lives with a background radiation dose that no population on Earth experiences, and the medical consequences will emerge over years and decades. And woven through all of these physical and medical challenges is the psychological dimension. It demands far more attention than it usually receives in discussions of Mars survival, because psychological breakdown does not merely affect the person experiencing it. It affects every system that person touches. 41 people confined together in a small, pressurized volume, knowing that no rescue is coming, watching systems degrade, rationing food and medicine, making daily decisions about which failing system gets the remaining spare part and which one they learn to live without. This is not an environment that produces ordinary stress. It produces a specific, grinding form of psychological erosion that researchers who study isolated and confined environments have documented extensively, even in simulations far less severe than what a Mars colony would face. Studies of long-duration isolation missions, including the Mars 500 simulation and NASA's first Sabatier mission, where 4 crew members spent 378 days in a simulated Mars habitat, have documented the psychological effects of confinement, communication delays, and resource limitations. Crew members in these simulations reported mood changes, sleep disruption, interpersonal tension, and periods of decreased motivation. And those participants knew the experiment would end. They knew they could walk out the door if things became truly unbearable. A Mars colony without resupply has no exit door. The absence of an exit changes the psychology fundamentally. On Earth, when a conflict becomes intolerable, people leave. They quit jobs. They end relationships. They move to different cities. Even in the most confining situations, the theoretical possibility of departure acts as a psychological pressure valve. On Mars, that valve does not exist. You cannot transfer to another facility. You cannot take a vacation. You cannot even go outside without a pressure suit, a power-consuming life support backpack, and a limited supply of breathing gas. The corridors of the habitat are your entire world. Interpersonal conflicts that on Earth resolve naturally through distance become chronic on Mars. Two crew members who develop a personal antagonism cannot be separated. They eat together. They sleep in adjacent quarters. They share the same air. Over months and years, unresolved tension does not fade. It hardens. It infects team dynamics. It creates factions. And in a colony where every task requires cooperation, where a single maintenance error can endanger everyone, factional division is not merely unpleasant. It is operationally dangerous. Then there is decision fatigue. The colony's leadership must make resource allocation decisions every day. Decisions that carry genuine life or death weight. The last replacement filter can go to the water recycler or the air handling system. It cannot go to both. The only remaining vial of a critical antibiotic can be used now on a crew member with a worsening infection, or it can be saved for a future emergency that might be more severe. There is no right answer. There is only a choice between two imperfect outcomes, made under pressure, with incomplete information, and with the knowledge that the people affected by the decision are watching you make it. On Earth, leaders in high-stakes environments rotate. Hospital administrators take vacations. Military commanders cycle through deployments. CEOs have boards to share the burden. On Mars, the colony leader makes these decisions every day, indefinitely, with no relief and no appeals process beyond the small group of people directly affected. The psychological weight of this responsibility is difficult to overstate. Decision-making quality degrades under chronic stress. The more consequential the decisions, the more stressful they become, and the more stress degrades the quality of the next decision. It is a feedback loop with no external circuit breaker. Grief adds another dimension that simulations cannot replicate. In a 41-person colony operating for years without resupply, people will die. Equipment accidents, medical emergencies, radiation-related illness. The first death in the colony will be a psychological earthquake. Not because the crew is naive about mortality, but because death on Mars carries a weight it does not carry on Earth. There is no funeral home. There is no extended family to share the mourning. There is no possibility of burying the person in a place that feels meaningful in the way a cemetery on Earth feels meaningful. There is a body that must be dealt with in a sealed habitat where biohazard management and emotional needs collide. And the death does not just remove a person. It removes a pair of hands, a set of skills, a role in the daily operation of systems that keep everyone else alive. The grief is compounded by the practical reality that the colony just lost capacity it cannot replace. The mourning crew member who takes over the deceased's maintenance duties is now doing two jobs while processing loss. In an environment where the normal human support structures for grief, community, ritual, distance from the source of pain do not exist. Over years, As the colony contracts and the toll of accumulated stress, injury, illness, and system degradation mounts, the psychological state of the crew becomes as much a survival factor as the condition of the reactor or the yield of the greenhouse. A crew that maintains cohesion, trust, and a shared sense of purpose can stretch resources further, improvise more effectively, and absorb setbacks without fracturing. A crew that fractures psychologically will make errors, defer critical maintenance, hoard resources, and eventually turn the slow contraction of the colony's material capabilities into a faster collapse. The psychological burden is not separate from the engineering challenges. A crew member who is depressed, sleep-deprived, or locked in a conflict with a colleague is a crew member who is more likely to make a maintenance error, miss a warning sign in the monitoring data, or delay a repair that cannot wait. Human performance degrades under chronic stress. The systems that keep the colony alive depend on human performance. Therefore, chronic stress is a systems-level threat, not merely a personal one. This is the landscape of the third survival layer. Food production that is fragile, limited, nutritionally incomplete, and vulnerable to catastrophic loss. Machinery that wears out on timelines measured in years and cannot be fully replaced with local manufacturing. Medical capability that shrinks with every treatment administered and every medication consumed. A dust environment that slowly poisons from the inside while it erodes from the outside. And a human element that is simultaneously the colony's greatest asset and its most unpredictable variable. Each of these layers interacts with the others in ways that compound the danger. A food shortage leads to malnutrition. Malnutrition degrades physical and cognitive performance. Degraded performance leads to maintenance errors. Maintenance errors lead to system failures. System failures divert resources from food production to emergency repair. The colony does not fail because of one catastrophe. It fails because of a tightening spiral where each problem makes every other problem worse, and the resources available to solve any of them are steadily declining. Somewhere in this spiral, the colony crosses a threshold that is invisible from the outside. It is the point where the rate of capability loss exceeds the rate of capability replacement. The point where the colony is no longer shrinking its dependence on Earth, but instead losing the ability to sustain what it already has. From that point forward, the trajectory has only one direction. What that trajectory looks like, how long it takes, and whether anything can arrest it before the colony reaches the end of its reserves is the question that remains. And answering it requires confronting the deepest challenge of all. Not whether the colony can keep its people alive for another month or another year, but whether 41 human beings on a hostile world can build the industrial foundation needed to survive not just this decade, but the next one, and the one after that, without a single shipment from the planet that made every tool they own. There is a concept in reliability engineering called mean time between failures. It describes the average interval you can expect between one breakdown of a system and the next. Every manufactured component has one. A water pump might have a mean time between failures of 20,000 hours. A pressure seal might last 5 years. A circuit board might function reliably for a decade before a solder joint fatigues or a capacitor drifts out of specification. These numbers are not guarantees. They are statistical expectations based on testing. Some units fail early, some last longer. But across a large enough population of identical components, the average holds. On Earth, Mean time between failures is a planning tool. You stock spare parts based on it. You schedule maintenance windows. You budget for replacements. When a pump fails ahead of schedule, you pull another one from the warehouse. The warehouse is restocked by a supply chain that stretches back to a factory, which is fed by raw material suppliers, which are connected to mines, refineries, and chemical plants, which are supported by transportation networks, energy grids, and a labor force of millions of trained workers. The mean time between failures is never the end of the story. It is the beginning of a replacement cycle that the entire industrial world cooperates to complete. On Mars, without resupply, mean time between failures becomes something else entirely. It becomes a countdown, not to repair, to loss. When the colony's last spare water pump reaches the end of its operational life, the colony does not place an order. It either builds a new pump from local materials using local tools and local expertise, or it accepts that water processing capacity has permanently declined. The pump does not come back. That capability is gone. Now picture this happening across every system simultaneously. Not at the same moment, but on overlapping timelines. The seals degrade on one schedule, the batteries degrade on another, the electrolysis cells on another, the medical supplies on another, the greenhouse lighting on another. Each system has its own countdown, and the colony is running all of them at once. Some clocks tick faster than others. Some can be extended with creative maintenance, but all of them are moving in one direction. This is the concept of irreplaceable capability loss, and it is the deepest threat facing a Mars colony cut off from Earth. Not the sudden disaster, not the explosive decompression or the reactor meltdown. Those scenarios are dramatic, but they are also the ones the colony is most prepared for. Emergency procedures exist. Redundancies are built in. The crew has trained for catastrophe. What the crew has not trained for, what no one can truly prepare for, is the quiet accumulation of small losses. The moment you realize that the medical scanner has been producing slightly unreliable readings for months, because a sensor has drifted and the calibration standard needed to correct it was used up last year. The day the fabrication workshop discovers that the last spool of vacuum-rated sealant compound has been consumed and the three-dimensional printer cannot produce a substitute because the polymer chemistry is wrong. The week when the greenhouse manager reports that the latest seed crop produced plants with noticeably lower yields than the previous generation, and no one can determine whether it is a soil nutrient issue, a lighting issue, or the early signs of genetic drift in a seed stock that has been recycled in a closed system for years without fresh genetic material. Each of these events is small. None of them triggers an alarm. None of them demands immediate evacuation, but each one subtracts something from the colony's capacity to sustain itself, and this subtraction is permanent. The colony does not bounce back from these losses. It absorbs them. It adapts. It finds workarounds. But the workarounds are always slightly less effective than the original system, and they themselves depend on other components that are also aging. From the outside, the colony might still look functional. The lights are on. People are moving through the corridors. The greenhouse is producing food. The reactors are generating power. A visitor arriving at this stage might report back that the settlement is doing well, but someone who had seen the colony a year earlier would notice the differences. Slightly dimmer lighting in one module where replacement LED panels were not available. A section of the greenhouse sealed off because the irrigation pump failed, and the remaining pump was reassigned to the larger growing area. A spacesuit hanging in the airlock, with a visible patch on the shoulder joint. Still functional, but no longer rated for the full pressure differential it was designed to handle. A medical bay where one of the diagnostic screens has gone dark because the display unit failed and the last replacement was installed somewhere else, where the need was judged more urgent. This is what slow failure looks like. Not a collapse, a contraction. The colony does not die. It shrinks. Its capabilities narrow. Its margins disappear. The distance between daily operations and the threshold of catastrophe closes, not through one dramatic event, but through 1,000 tiny reductions that nobody planned for because they were each too small to appear on any risk assessment. To arrest this contraction, the colony would need to do something that no group of 41 people has ever done in the history of the human species. It would need to build an industrial ecosystem from the ground up on a planet with no existing infrastructure, using only the raw materials available on the Martian surface and whatever tools and knowledge were included in the original mission. Consider what an industrial ecosystem actually means. On Earth, producing a single integrated circuit, the kind found in every computer, sensor, control system, and communication device the colony depends on, requires a fabrication facility that costs billions of dollars, operates in a clean room with air filtered to a few particles per cubic meter, uses photolithographic processors operating at nanometer scale precision, depends on dozens of specialized chemical inputs, including ultra-pure silicon, doping agents, etchants, and photoresists, and draws on a global supply chain of raw materials sourced from mines on 4 continents. The entire sequence, from raw silicon sand to a functioning chip, involves thousands of individual process steps perfected over decades of industrial development. A Mars colony cannot build a semiconductor fabrication facility, not with 41 people, not with 3-dimensional printers and Martian regolith, not in a decade. The electronics the colony depends on are artifacts of an industrial civilization that took centuries to develop, and they cannot be replicated in miniature on a world where the first priority is staying alive tomorrow. And electronics are not the only irreplaceable category. Consider pharmaceuticals. On Earth, the production of even a common antibiotic like amoxicillin requires a fermentation facility where carefully maintained strains of specific fungi or bacteria are cultured under precise conditions to produce the raw compound. That compound is then extracted, purified through multiple chemical separation steps, formulated into a stable dosage form with binders, fillers, coatings, and preservatives, tested for potency and contamination, and packaged in airtight containers that protect it from moisture, light, and oxidation. The raw chemical inputs for the process come from specialized chemical suppliers. The culture organisms must be maintained in stable conditions or stored in cryogenic banks. The analytical equipment used for quality testing, spectrometers, chromatographs, dissolution testers, is itself a product of advanced manufacturing. A Mars colony cannot build a pharmaceutical production facility any more than it can build a semiconductor fabrication plant. It can store medications brought from Earth. It can ration them carefully. It can extend some shelf lives through proper storage. But it cannot synthesize new drugs from Martian raw materials using equipment designed for other purposes. When the antibiotics expire or run out, the colony does not transition to locally produced alternatives. It transitions to a world without antibiotics. That sentence deserves a pause. A world without antibiotics. Before the discovery of penicillin in 1928, a simple infected cut could kill. A dental abscess could become sepsis. A compound fracture that broke the skin was frequently a death sentence. Surgical procedures that we consider routine today, appendectomies, cesarean sections, repair of internal injuries, were far more dangerous because post-operative infection could not be reliably controlled. A Mars colony that has exhausted its antibiotic supply returns to this era of medical vulnerability, except that the population is smaller, the environment is harsher, the wounds are more frequent, and there is no prospect of the situation improving. This is not a failure of imagination or ambition. It is a physical constraint. Manufacturing advanced technology requires not just knowledge, but infrastructure. A machine shop requires precision cutting tools. Precision cutting tools require hardened alloy steel. Hardened alloy steel requires iron ore, carbon, chromium, tungsten, and a furnace capable of reaching temperatures above 1500 degrees Celsius, with precise atmospheric control. The furnace requires refractory bricks. The refractory bricks require specific mineral compositions. Each step in the chain requires the output of a previous step, and the chain stretches back to raw geology. Mars does have raw materials. The regolith is rich in iron oxide, silicon dioxide, aluminum oxide, and other minerals. Water ice provides hydrogen and oxygen. The atmosphere provides carbon dioxide. In principle, these can be processed into useful materials. Iron can be smelted from regolith. Silicon can be extracted. Concrete-like building materials can be produced using sulfur or polymer binders. In situ resource utilization research has demonstrated many of these processes in laboratory settings on Earth. But demonstrating a process in a laboratory and operating it at industrial scale on Mars are vastly different challenges. Laboratory demonstrations use precision equipment manufactured on Earth. They operate in controlled environments with stable power, temperature, and atmospheric conditions. They are performed by researchers who can walk to a supply room for a missing reagent or replace a broken piece of glassware from a catalogue. Scaling these processes to produce the volume of materials a colony needs for self-sustaining manufacturing, while simultaneously keeping the colony alive, while maintaining all of the systems, while operating in a hostile environment with a crew of 41 people who must also eat, sleep, maintain their health, and manage their psychological well-being, is a challenge of a fundamentally different order. The realistic timeline for industrial self-sufficiency on Mars, if it is achievable at all, is measured in decades to centuries. A colony that has been cut off from Earth does not have decades. It has the lifespan of its least replaceable critical system. And that lifespan, for the most complex components the colony depends on, is likely measured in years. This brings us to the timeline question that sits at the heart of this entire story. How long could a Mars colony actually survive without Earth? The honest answer is that there is no single number. The timeline depends on what the colony has, how much of it there is, how well it was designed, how skilled and adaptable the crew is, and which systems fail first. But we can draw rough boundaries based on the dependency layers we have walked through. In the first weeks to months, survival is determined by the first layer: pressure, oxygen, carbon dioxide removal, temperature, and power. A well-designed colony with functioning systems and stockpiled spares can handle this layer. The crew knows the emergency procedures, the redundancies are in place. Barring an immediate catastrophic failure, the colony survives this phase. In the first 1 to 3 years, survival is determined by the second and third layers together. Water recycling efficiency, ice extraction capability, food production, and the rate at which spare parts and consumables are being drawn down. This is the phase where the margins begin to narrow. The crew is adapting, improvising, and stretching resources. Systems that were designed for 5-year lifespans are being pushed toward their limits. The greenhouse is producing food, but not enough to replace stored reserves entirely. Medical supplies are being rationed. The colony is alive, but trending in a direction that is not sustainable. In the 3 to 10-year range, survival depends on whether the colony has managed to establish reliable local resource extraction and basic manufacturing. If it can mine ice, produce oxygen, grow enough food, and fabricate simple replacement parts, it can stabilize at a reduced but functional level. If it cannot, the contraction accelerates. Systems that kept other systems running begin to fail, and the cascading effects described earlier propagate through the entire network of dependencies. Beyond 10 years, survival becomes a question that no amount of engineering analysis can confidently answer because the variables are too many and too uncertain. Can the colony replace its reactor fuel or build a backup power system? Can it maintain genetic diversity in its seed stock? Can it manage the long-term health effects of radiation, low gravity, and nutritional stress? Can it sustain the social cohesion and institutional knowledge needed to keep an industrial operation running with a population smaller than a single classroom building at a university? The question is further complicated by the fact that the colony's population is not stable. People die. Over a decade, even in the best circumstances, injuries, medical emergencies, and accumulated health effects will reduce the headcount. Every person lost is not just a life, but a set of skills, a body of knowledge, a pair of hands that maintained specific systems. If the colony's only person with deep expertise in reactor maintenance dies from an infection that could have been treated with an antibiotic, the pharmacy no longer stocks. The reactor does not care about the cause of death. It only knows that the person who understood its most delicate systems is no longer available. The knowledge dies with them unless it was thoroughly documented, and another crew member was cross-trained. In a 41-person colony stretching to cover hundreds of specialized roles, cross-training gaps are inevitable. Reproduction introduces another dimension entirely. If the colony is to survive beyond the lifespan of its original crew, children must be born and raised. Human reproduction on Mars has never been studied. We do not know whether conception, pregnancy, fetal development, and childbirth can proceed normally in 38% gravity. Animal studies suggest that reduced gravity affects embryonic development, bone formation, and cardiovascular system maturation. A pregnancy on Mars carries risks that no obstetrician on Earth has ever had to consider. Managed in a medical facility with a fraction of the resources available in even a small rural hospital. The unknowns are staggering. During pregnancy on Earth, the cardiovascular system adapts dramatically. Blood volume increases by roughly 40 to 50%. The heart works harder. Blood pressure fluctuates. These adaptations evolved under one specific gravitational load, the load this planet provides. In 38% gravity, the body's fluid dynamics are different, blood pools differently. Fluid shifts toward the head instead of distributing normally. We have no data on how the pregnant body handles these shifts over 9 months, whether placental development proceeds correctly when the blood supply is distributed by different gravitational rules, or whether the fetus receives adequate oxygen and nutrients through a vascular system operating under conditions it was never designed for. Childbirth itself presents risks that would be manageable in a well-equipped hospital and potentially catastrophic in a Mars medical bay. Hemorrhage during or after delivery is one of the leading causes of maternal death worldwide, and on Earth, it is managed with blood transfusions, surgical intervention, and specialized medications. A Mars colony has no blood bank. It has no operating room in the full surgical sense. It has medications that may be expired or unavailable. A delivery complication that is routinely survivable on Earth could be fatal on Mars, and the death would remove not only a crew member, but the infant she was carrying, both at once. If a child is born alive and healthy, the questions multiply rather than resolve. DNA repair mechanisms in human cells are calibrated for Earth's radiation environment. A child developing on Mars is exposed from the moment of conception to a radiation dose that no developing human has ever experienced. The long-term effects on cellular development, cancer risk, neurological maturation, and immune system function are completely unknown. There is no dataset. There is no precedent. The first child born on Mars would be a biological experiment with a sample size of 1, conducted in an environment where the consequences of failure cannot be corrected. That child's skeletal and muscular development would proceed under gravitational conditions that produce a fundamentally different body. Bones form their density in response to the loads placed on them. Muscles develop their strength against the resistance they encounter. A child who grows up in 38% gravity would develop bones roughly calibrated for that load, not for the roughly 2.5 times stronger pull that Earth's surface would impose. Their cardiovascular system would condition itself for pumping blood against Martian gravity, not Earth's. Their vestibular system, the inner ear structures that govern balance and spatial orientation, would calibrate to a world where objects fall more slowly and way less than they would on the planet their parents came from. Such a child might never be able to visit Earth. The transition from Martian gravity to terrestrial gravity would impose forces their body was never built to handle. Their bones might fracture under their own weight. Their cardiovascular system might be unable to maintain blood pressure in a standing position. They would be, in a very real biological sense, the first true Martian, a human being native to another world, and their entire existence would depend on systems built by people from a planet they could never set foot on. Raising children in a contracting colony introduces a moral dimension that goes beyond engineering. Adults who chose to live on Mars accepted the risks with informed consent. A child born into the colony made no such choice. They inherit a world they did not select, with constraints they cannot escape, in a settlement whose future is uncertain. The educational, emotional, and developmental needs of children are not optional additions to the colony's workload. They are fundamental requirements that consume resources, crew time, and psychological energy at a stage when all three may be scarce. And the children themselves, as they grow, represent the colony's only path to long-term survival, because without a next generation, the settlement ends with the lifespan of its original crew, regardless of how well the machinery holds up. Here, at the far end of this analysis, the question stops being purely technical and becomes something harder to answer with equations. What does it mean for a group of human beings to be truly alone? Not alone in the way an astronaut is alone on a spacewalk, tethered to a vehicle that will bring them home. Not alone in the way a polar expedition is alone, knowing that rescue will come when the weather breaks. Alone in a way that no community of humans has ever experienced. Separated from every other living person by a minimum of 34 million miles of vacuum, and a communication delay that makes real-time conversation impossible. Knowing that every resource they will ever have is either in their hands already or locked inside a planet that yields its materials only under the most extreme persuasion. There is something in this thought that goes beyond survival mathematics. It touches the deepest question of what human civilization actually is. We tend to think of civilization as a set of ideas, laws, cultures, and traditions. But underneath all of that, civilization is a material infrastructure. It is mines and factories and roads and power plants and hospitals and farms, an interlocking web of physical systems so vast that no single person can comprehend its full extent. We live inside this web without seeing it, the way a fish lives inside water without knowing what water is. A Mars colony cut off from Earth is a group of human beings who have been pulled out of that web and asked to build a new one from raw geology, with a team smaller than the staff of a moderate-sized restaurant, on a world that provides no air, no water at the surface, no warmth, no shielding, and no forgiveness. The colony's survival does not depend on heroism, although it will require plenty. It does not depend on genius, although brilliant improvisation will be necessary every single day. It depends on whether a tiny group of people can outrun the rate at which their manufactured world decays. It is a race between human ingenuity and entropy, between the drive to build and the tendency of all complex systems to break down, between the will to survive and the patient. Indifferent hostility of a planet that has been dead for billions of years and does not care whether anyone lives on it. The terrifying answer is not that a Mars colony would die instantly without Earth. It would not. The first weeks would be tense but manageable. The first months would be difficult but survivable. The first year would be a testament to human resourcefulness and determination. The terrifying answer is that the colony could survive long enough to seem independent. Long enough to grow food and recycle water and generate oxygen from the Martian atmosphere. Long enough for the crew to begin thinking of themselves as settlers rather than castaways. Long enough for the word colony to feel earned. And all the while, beneath the surface of daily life, the inventory of irreplaceable components would be dwindling. The medicines would be expiring. The seals would be aging. The electronics would be accumulating the micro damage of radiation and thermal cycling that eventually makes a circuit board produce wrong answers instead of right ones. The countdown would be running beneath every operational system, invisible until the moment it reaches zero. A colony that cannot replace the machines that keep it alive is not a settlement. It is a clock, built from the most extraordinary engineering human beings have ever produced, ticking in a direction that cannot be reversed with willpower alone. This is why the question posed at the beginning of this story does not have a simple numerical answer. Asking how long a Mars colony could survive without Earth is like asking how long a fire can burn without fuel. The answer depends on how much fuel you start with, how efficiently you burn it, and whether you can find more before the last ember dies. The colony starts with a tremendous stockpile of engineered fuel. Machines, materials, knowledge, and human skill. It burns through that fuel at a rate determined by the environment, the quality of its systems, and the competence and luck of its crew. And whether it can find new fuel Whether it can build the industrial foundation to produce what it consumes is the question that decides everything. The most likely truth, based on the current state of technology and the known constraints of the Martian environment, is that a well-prepared colony could survive for years. Perhaps many years if the crew is extraordinary and the initial stockpile is generous. But surviving for years is not the same as surviving indefinitely. And the distance between those two outcomes is the distance between an outpost and a civilization. The difference between an outpost and a civilization is not population size or territorial control. It is the ability to sustain itself through its own production. A civilization makes the things it needs. An outpost receives them. Every colony in human history that became a civilization did so by developing local industry, local agriculture, local governance, and local knowledge sufficient to stand on its own. Every outpost that failed to do this eventually collapsed when its supply line was severed. Mars will not be different. The physics is different. The chemistry is different. The distance is different. But the underlying logic is the same. A group of human beings cut off from external support will survive for as long as their stored reserves and repair capacity allow, and not one day longer unless they build the means to replenish what they consume. The true test of a Mars colony is not the first landing. It is not the first harvest from Martian-grown crops. It is not the first breath of oxygen extracted from the Martian air. All of these are extraordinary achievements. All of them deserve celebration. But none of them answer the question that matters. The true test comes on an ordinary day, months or years after the celebrations have faded, when a technician reaches for a component that the colony cannot function without, and the storage bay is empty, and Earth is a bright dot in the Martian sky that cannot hear the request, and could not answer it if it could. What happens in that moment is the answer. Not to the question of how long a Mars colony could survive without Earth, but to the question of whether human beings can truly live on another world, or whether we will always be visitors, sustained by an invisible thread stretching back across millions of miles to the only planet that has ever kept us alive. That thread is thinner than we think, and Mars is more patient than we imagine. It does not need to kill us. It only needs to wait for the last machine we cannot rebuild to finally stop working. And on the day, the silence of Mars will not be the silence of an empty world. It will be the silence of a world that was asked to become a home and answered the only way it knows how. With cold, with dust, with time.